Welcome to Ask and Learn.
Okay, so for this problem, it's discussing car engines. Not something I know a lot about, and so I'm kind of glad I learned about it through doing this problem. And so, yeah, it just talks about like basically how if you get more mass into the engine, then like your power output is greater. And so the first question. Well, first you just want a PV diagram of the process. So like I'm going to kind of summarize the question as I make this PV diagram. So here's P and here's V. So you start out at a high volume, compress adiabatically to a lower volume, and then you like let it cool just a little bit. So you go to a lower isotherm. And I'm going to label these states 1, 2, and 3. Okay, so easy part. Now on to the more challenging part. Okay, so I had to read okay, so the next one, first of all, it just asks, let's see, sorry, I'm going to review the question. It asks what the mass of air is filling the cylinder. So and then like what's the power output increase from getting all this extra mass if you like didn't have this turbocharger and intercooler process. So this problem I had to read like 50 times just because like it was new vocabulary. So and I saw the solution and like I just like it did not make sense until I thought through it myself. So if this is hard to follow, I encourage you just to like gather your own thoughts on the problem. And then a helpful thing that I made to help me get my little vocab straight was to make like a little diagram for the process. So it's like you get the air in from the turbocharger, and then that goes to the intercooler, and I'm not going to draw another box. I'm going to draw a cylinder. So here's our cylinder. And I'll just label it so. And then this is the thing that's like this V cell, which is 575 centimeters cubed. And so I'll just note over here, I just wrote down like all the givens. It's air, so the gamma is 1.4 because it's basically nitrogen. Kind of implicit in the problem. You have to know that. And I also converted the units of the volume of the cylinder from centimeters cubed to meters cubed. So that's 100 centimeters per meter. And then you do that conversion 3 times, and then you get something like this. And so you have to cube that 100 when you're dividing. Okay. So yeah, the calculation isn't hard, but I feel like this one was like a little bit like you had to think about it for a second. So I convinced myself that what I did was right. So hopefully I'll be able to kind of say it back in the proper way. So yeah, basically like you're starting out with this not dense air, and then you have the dense air, and like how much of it is gonna fill this cylinder. So so one thing I started by acknowledging that like you're gonna have the same number of particles and going from state 1 to 3, and so if you use that, you could if you use that and you use like your knowledge of how thermodynamic quantities like pressure, volume, stuff change through different processes, then you can figure out like what's going on with the density. How is the density changing? Because once you know how the density changes, then you kind of know how the mass changes. So there's probably like tons of different ways to and think about this, but this is just like what came to me, so I'll explain that. So we know PV. Oh, I already wrote B. Okay, so we know that PV is nRT. And so I like to just like put on one side of an equation things that stay the same. So in going from 1 to 3, completely ignoring that this process in 2 happens, I'm pretending that there's the machinery to go directly isothermally from 1 to 3, which, yeah. So from 1 to 3, N, R, and T are like all the same. So then you can get what's going on with the volume. And so you can say that P1 V1 equals P3 V3 because of that, because they're both equal to nRT, and that stays the same. So what you can do is you can get the volume at 3, and that's just P1 over P3. Oh, we already know the volume at 3. So we want the volume at 1 because we like want to know how much, we're starting with. I guess it's kind of implicitly finding the size of like whatever the tank is for the turbocharger. So anyway, so you get P3 V3 over P1. And of course we expect this to be larger than the original because we're going to compress it. And indeed, so if you do this, I don't know if I actually calculated it. No, I didn't. Okay, but I kind of just like did it all at once. So anyway, I'm just gonna like leave that off to the side. So we know how to get the different volume. So we have the volume at 1. So we can get, so great, we're like basically done now for this part because you can get the mass. So since we know the density of air, you know the volume that was captured, and you know the density, you can get the mass that was captured. And so then you can get that mass is equal to rho times V at 1. And then we're kind of backing out that V at 1 is this. So there's our rho. V at 1 is this P3 over P1. Sorry if my P's and rhos like look so similar. They don't look similar to me, but I'm very used to seeing these symbols. Okay, and I'm just gonna like look at my math real quick and make sure that it makes sense. Okay, so great. If you do that, then you get 1.02 times 10, to the minus 3. Yeah, so and then another way to read this off is to think about this is that like, well, kilograms. Another way to think about this is that the you can just figure out that the density is going to increase by P3 divided by P1 just based on this P1 V1 equals P3 V3. And I think thinking about that proportionality will be helpful for part C. Okay, and so then they're asking like, okay, well, what is the increase in power? You percent-wise, so you have to acknowledge in the beginning of the question, they tell you like power is proportional to mass. So basically the question is like, how much more mass are you getting in there? And so if you didn't have the turbocharger, so unfortunately I have to do a new board. Like if you didn't have the turbocharger, like your mass would just be just rho times the volume of the cylinder. And so if you calculate that, then maybe you'll get what I got. Where did I get that? Must be on the next page. Oh, here it is. Okay, sorry. So that's 7.07 times 10 to the minus 4 kilograms. So the percent increase is just going to be a ratio between those two. So that's just your, so I'll label that percent increase equals 1.02 times 10 to the minus 3 kilogram divided by 7.07 times 10 to the minus 4. Sorry, let me just double check something. Oh, sorry, and then minus 1. My bad. Minus 1 equals 44%. So, yeah. And part C talks about, well, what would happen if you just cut the intercooler out of the equation. And again, it's a question of like, well, what is the density? What would be the density of the gas after this process? So I'll admit I thought about this a lot, and this is the simplest way to think about it. But maybe sometimes it's a good idea to meander through the not simplest way to think about it. But I think this works. So our goal is to get how does our number density change, right? Because once the number density is proportional to the real density, to the mass per kilogram per meter cubed density, because the mass per particle is the same. So if we can just find this ratio, then we can figure out how to get the new density of the gas just as it's going into the cylinder. And so, yeah, if you do this ratio and then you use the ideal gas law, you'll find that this ratio is P1 over P2 times T2 over T1. So let's think about that. We have the initial pressure, we have the final pressure, have the initial temperature because it starts at room temp, or is it room temp? Oh, it's cold. It's like 15 degrees C. Did I put that actually on the last one? 15 degrees C. Oh, I didn't actually write that, but that's okay. I'll put it here. So it's 15 degrees C, and then if you need to add 273 to that to get the Kelvin. So, yeah. But we don't have T2. So back to the problem, we don't have T2. How can we get T2? We can get that just through the adiabatic relationship between quantities for an adiabatic process. So then for that, you would do T2 is T1 times P2 over P1, gamma minus 1 over gamma, and that's in the book for adiabatic processes. So I'm going to guess that if you're like doing this problem, you've probably done a bunch of the earlier ones. So I'm going to kind of skip some, not totally hold your hand through it. So yeah, so if you plug that T2 in there and like, right, you know your T1, that's 15 degrees C, 288, you know that ratio, P2, P1, the P2 is the 1.45, 10 to the 5 pascals, and you know your gammas, gamma is your 1.4, and your P1 is your atmospheric pressure. Whoops, didn't mean to make that line. Okay, so you know your T2, you plug it in there, and then you can get that ratio, and then that ratio is, I think it was 0.77. Let me double check. 0.77. So then that means that it's so that's how much it would decrease, I guess, if it went from the cylinder to just air. So it increases by the inverse of that, the density increases by 1 over 0.77. And so finally, you know that if that's how much the density increases, then the mass is just that times 1 over 0.77. This is your 1.23, and times the volume of the cylinder, which is our 575 times 10 to the minus 6. Yeah, 100. to the minus 3, 10 to the minus 6 meter cubed. And this 1.23, let me put some units on that, kilogram meter cubed. And so, yeah, then maybe you'll get what I got, which was, where did I write down that number? So that's 9.14, 10 to the minus 4 kilograms. And then to get the percent change, you want to compare that to 9.14, 10 to the minus 4 kilograms to what you would have gotten otherwise. So our 7.07 times 10 to the minus 4 kilograms minus 1. And then let me just double check that. So 30%. So the engine is not doing as good as it would be if it didn't have to use colder air. So yeah, the engine would be better if it didn't have to use cooler air. So it was an increase of 30%.